And welcome to the third lecture of chapter 3, where we finally get to talk about stoichiometry and all the cool math that we can do with chemicals. Yeah. Okay, so we finished the last lecture slides of chapter 2 with this slide. And I just wanted to bring it back up to really drive home some of the key principles that make these like mole ratios so important and why we use moles to begin with. So here we have a chemical reaction. It's already balanced for you. And we talked about how we have this mole ratio that's represented by our coefficient. Remember, the absence of a coefficient means that there is 1 mole versus 2 moles for LiOH. So just as a quick review, going back to lecture 1 of this chapter, remember that 1 mole is equal to 6.022 times 10 to the 23rd units. Right, so when we're talking about stoichiometry, a unit is either going to be a molecule, or we can also just call that a compound. I'll use both kind of interchangeably. Or it could be, right, just like an atom. So sometimes we'll have chemical reactions where we're just looking at a metal ion, for instance, that's interacting with other species. So it doesn't matter what the identity of those units is. If you have 1 mole, it is 6.022 times 10 to the 23rd of them. So the mole does a great job of creating this equal playing field. So it's an equalizer between everything, in the same way that like a dozen is. So if you have a dozen chairs, you have a lot of chairs. If you have a dozen marbles, maybe that's a lot of marbles, but it's definitely taking up a lot less space than a dozen chairs, but you still have a dozen of both. So weird analogy, but that's the same thing that a mole is doing. So it doesn't matter how big the molecule is, how complicated it is, how many grams it weighs. 1 mole and 1 mole of a species, you're going to have 1 molecule for 1 molecule. And that's what we're interested in when we're talking about stoichiometric reactions, right? When we're talking about how much of something do we need in order to produce the amount that we want. Usually that's the way that we're going. So just to kind of further illustrate this point, if we were to look at this reaction in terms of the molar mass of each component, we would have LiOH is 23.9 grams per mole, carbon dioxide is 44 grams per mole, lithium carbonate is 73.882 grams per mole, and water is 18 grams per mole. Okay, so we have this big variety in the mass of 1 mole of each of these compounds, right? And so what I'm trying to drive at here is that our relationships that our coefficients are demonstrating is only at the mole level, not at the gram level. So when you look at like lithium hydroxide and carbon dioxide, you know, you're like 23.9 and 44, that's almost like twice as much, but that relationship breaks down entirely when you look at lithium carbonate. So whenever you're comparing one species to another, you cannot be in the realm of grams. Grams is relative. Moles means 1 for 1, 1-to-1 ratio. So it's just like really, really critical to understand before we move on to stoichiometry. So from this equation, we're given a ton of information about this reaction. So we know that we need 2 molecules of lithium hydroxide for every 1 molecule of carbon dioxide to produce 1 molecule of lithium carbonate and 1 water molecule, right? Mole ratios, 1 molecule for 1 molecule for 1 molecule. So from this, we could write a lot of mole ratios. So mole ratios is telling you that relationship on the scale of moles between 2 species. Again, moles is really the only time where we can compare them fairly. So one example of a mole ratio would be between our carbon dioxide and our lithium hydroxide. So we have 1 mole of carbon dioxide for every 2 moles of lithium hydroxide. Now, this is essentially an equivalency statement. Or let's actually call it just a conversion factor. Right, and this conversion factor is specific to the balanced chemical reaction. Right, you might have a more complicated reaction with lithium hydroxide and carbon dioxide that would have a different mole ratio, but that's a different chemical reaction. They're not comparable. You could also write a factor of like 1 Li2CO3 for every 1 H2O. Right, so from this chemical reaction, we can write a lot of mole ratios, and that's going to become really important in our flow of problem solving. So all stoichiometric problems break down to basically this flow, and I'm going to also give you guys kind of my version too. So this is straight from your textbook. Oh, excuse me. So you have the mass of compound A, so this would be like whatever you're interested in. And then you convert your mass to moles, right? Because moles is where we're equaling, we're making the playing field equal. So you're converting from mass to moles. Once you're in the realm of moles, then you have the ability to use mole ratios, right? What is a mole ratio? It is allowing you to convert from one species in a chem reaction to another. Right, in much the same way as our like unit factors allowed us to do that in chapter 1 material. So using that mole ratio, we are able to go from talking about compound A to talking about compound B. Once we know the moles of B, it's just molar mass to get to the mass of compound B. This flow is essentially what every stoichiometry problem breaks down to. So the way that I like to kind of think of this is in your stoichiometric problem solving strategy, you're going to have this basic flow. So first you need to write a balanced chemical reaction. So in doing that, you need to remember to write balanced, or I'll just say correct, chemical formulas, right, for each species. Super important. Then you'll convert mass to mole, right? We're never making a comparison between two species in the unit of grams. Not in stoichiometry. To make these conversions, right? So then we use our mole to mole ratio, otherwise just known as a mole ratio, to transition. This is the big idea here. It's a transition between species. So this is the only way to go from talking about one species to talking about another. And then you can convert to a desired unit. So we're going to do a few problems here because that's really the only way to get chemistry down. And it's super important that you promise a lot of stoichiometry problems because that's basically all chapter 3 and 4 is from this point on. And it's all just going to be kind of elaborating on these concepts. So yeah, do it. Practice. There's a ton of worksheets. Yeah. Okay. So the reason why this is stoichiometric problem is to remind me to go to this screen. Okay, so here the balanced chemical reaction is already given to you. You have V2H6 and oxygen combining to form HBO2 and and water. Okay, so the question here is what mass, let me get my pen out. Pretty sure we don't want a yellow color. Let's go through it. So what mass of oxygen, oh, that's fine, is needed to burn this many grams of C6, of, B2H6. Okay, so we have that flow, right? So you're gonna go from mass to mole, then you go mole ratio, right? So this is like compound A, moles of compound A. Mole ratio allows you to go from A to B, and then that gives you your moles of B, and you go back around to mass of B. So I'm going to leave that there just so we can see that really that's all we're doing with this problem, which at first glance for a first stoichiometry problem, you might be like, ugh, I don't like it. Right? What you'll learn in chemistry is that those, I don't like it, like knee-jerk reactions, you just get more comfortable with them and you become more creative in your problem solving. And you get to the point, hopefully, where you do enough practice problems or when you see a new kind of question on an exam, you know that you have the tools to answer that question. I would never give you a question that's outside of the scope of what you've learned, right? So working through problems is what allows you to develop familiarity, allows you to start getting more creative with your problem solving. Okay, so what mass of oxygen is needed to burn 36.1 grams of our B2H6? All right, so mass of A, 36.1 grams of B2H6. So I need to go from grams of B2H6 to moles of B2H6. I'm just going to write out kind of our path and then we'll fill in these numbers as we go forward. So then we have our moles of B2H6 is going to be canceled out with our moles of, what are we looking for? Oxygen. And then we go from our moles of oxygen to our grams of oxygen. Right, so this is giving us kind of a roadmap of where we're going. This is just kind of an alternative way to work these problems. Some students really like doing this because you can see, okay, grams of my B2H6 cancels out with grams of B2H6. Moles of B2H6 cancels out with moles. Moles of oxygen cancels out with moles of oxygen, right? Leaving us with grams of oxygen. So that can be a nice way to be like, okay, did I cancel things out? Did I properly transition from one species to another? Okay, so now we need the actual quantitative data, right? What we're interested in. So if you don't have it out already, you should have your periodic table. Yeah, do. Okay, so boron, 10.811. I have 2 of those atoms in each mole of my B2H6. I have 6 hydrogens, so that is 27.62. And that is going to be in 1 mole, right? We are always finding the molar mass just of 1 mole. It doesn't matter what your coefficient is here. You do not include that when you're looking at your molar mass transitioning from grams to moles. Why? Because that's going to be included in this mole ratio. So we see from our mole ratio, that's my B2H6. We're going to oxygen. We have 4 oxygens. So that is a 1 mole of B2H6 for every 4 moles of oxygen. So what does that mean? It means I need 4 times as many molecules of oxygen as I need B2H6 in order to move my reaction forward. So again, always when you're going from grams to moles, it's just 1 mole. And then O2, 16 times 2 is 32. Okay, so now we're just going to multiply across and divide by the product of the denominator. All right, so that is the mass of oxygen that is needed to burn 36.1 grams of B2H6. All right, so let's see this next question. How many moles of water are produced from, I don't know why that stopped working. That much, it's not working for some reason. This much of our B2H6. Okay. So now we're looking for moles of water. So this is cool, right? We'll go from grams of B2H6, so that's going to be A again. But then we get to just stop at moles of B2, which we love, right? It's one less step. Even though we already know the molecular mass of water is 18 grams per mole, but that's okay. So we have 19.2 grams of B2H6. And now we'll do it stepwise, right? So we know from solving this problem that there's 27.62 grams of B2H6 in every 1 mole. And now we are looking at the relationship between B2H6 and water. So it's 1 mole of B2H6 for every 2 moles of water, right? And that's actually as far as we need to go because the question is in moles, which is unusual, but we'll take what we can get. Usually you have to convert to moles. All right, and we get, convert to grams, and we get 1.39 moles of H2O. Right, if we were converting to grams, then it would just be 1 mole of water, 18 grams. Because there's 18 grams per mole, so we just take that number and multiply it times 18, and you get 25.03 grams of water. Right, and because we know that the density of water is about 1 gram per milliliter, you could also say that that's 25 milliliters of water produced in this combustion reaction. Very cool. Okay, so that's one example for us. We're going to work through another one. I'm just going to cut and paste it and bring it over to our next, to that same program. All right, no problem. There we go. Okay, so we have solid lithium hydroxide is used in space vehicles, cool, to remove exhaled carbon dioxide from the living environment by forming solid lithium carbonate and liquid water. That's cool. Right? Because you don't want carbon dioxide to build up. Not good for cells. What mass of gaseous carbon dioxide must be absorbed by 1 kilogram of lithium hydroxide? And look, we already have our balanced chemical reaction there. Going easy on you guys. Okay, so we have 1 kilogram of lithium hydroxide. And the question is, how much carbon dioxide can be absorbed? Right, so this would be compound A, that's compound B. Let's do it. Okay, so we know that we have 1 kilogram, and our molar mass is going to be in grams per mole. So I'm just going to change that to 1,000 grams. And let's see, what is the molar mass of lithium hydroxide? 6.941. I think I had that on the last slide. Yeah, it's 23.9. Oh. All right, now we're going to use the mole ratio of lithium to our CO2. I would recommend that when you're working through stoichiometry problems, you always want to keep both your number and your unit, so like 2 grams, and your species. So it's really good to be able to see that lithium hydroxide is canceling out here. That's probably the number one mistake that students make. Okay. Right, so we had grams, just to kind of go through that flow. It never really changes. It's just gonna get a little bit more elaborate, but that's it. So we have grams of one species. We're transitioning from grams of that species, sorry, that was supposed to be in red, grams of that species to moles, right? Then we use our mole ratio from our chemical reaction to transition from one species to the other. And we use molar mass to convert from grams to mole again. All right, so we have 1,000 times 44 divided by the product of 23.9 times 2. Oh. So 920.50 grams of CO2. Very cool. I was gonna say something. This is our answer. I don't know, it'll come back to me. All right, so it's just another kind of simple problem for you to kind of review, try to solve it on your own, make sure that you get to the same point. Oh, right, this is what I was gonna say. So if you didn't obey the order of operations here, and you just plugged it in as like, without dividing by the product, you would get a really large number, which you should immediately be like, huh, that seems like curiously high. So follow the order of operations is the take-home message there. Okay, so everything that we've talked about so far, we've been looking at the amount of one reagent that we have, right? So one thing I don't think I've said yet is that, you know, all chemical reactions go reactant to product. So reactant to product, right? We sometimes say reactant, we also say reagent. They're equivalent words. So if you hear me say reagent, it's just, I don't know if it's older. It's what my chemistry teacher in high school used. That's what I use. Okay, so probably, well, no, it's not older. It's just what she preferred. She was awesome. Little bit of an influence on me. Okay, so limiting reagents is going to be really important for us to consider in situations where you're given information about 2 reactants and you're asked to find information about a product. So just going back quickly to like our last problem, let's just pull it up really quick for review. So here our question was, what was our mass of CO2 generated from this much of our reactants? So these were questions about 2 reactants, right? So limiting reagent doesn't come into play in that. That's not what we're interested in. But it will come into play if you're asked or given information about 2 reactants and asked about a product. So again, last example we're just asked if you have this much reagent, how much of the other reagent do you need? So limiting reagent is basically this idea that you're always going to run out of something before you run out of the other. So here we have the reaction between nitrogen gas and hydrogen gas to form ammonia, right? So that would be H2 plus N2 forming NH3. Let's go ahead and balance that. right? Because otherwise it would drive me crazy. Okay, so you need 3 times as much hydrogen as nitrogen in order to produce 2 moles of our NH3. So here is a vessel before the reaction, and it's showing us the quantity of our H2 and our N2s that we have. So notice for these nitrogens, we have enough hydrogens in order to form our 2 ammonias. But we have these 2 remaining nitrogens that are left over, right? There's not enough hydrogen for ammonia to form. Because of that, we would say that hydrogen is the limiting reagent or reactant. Why? Because hydrogen limits the amount of ammonia that we can produce, right? We still have nitrogen, but it doesn't matter. We don't have the hydrogen necessary to create our compound. So this is an excess. Hydrogen is our limiting reagent. So I usually like to use the analogy of like if you were given a loaf of bread in a jar of peanut butter and you really like peanut butter sandwiches, and each peanut butter sandwich requires 2 slices of bread and some peanut butter, right? Now, depending on your style of peanut butter sandwich, if you're like my nephew and you put like 2 inches of peanut butter on, you're gonna run out of peanut butter way before you run out of bread. If you're like a logical person and you use much less peanut butter than that, you're probably gonna run out of bread before you run out of peanut butter, maybe? I don't know. If you were perfect in your allocation of peanut butter to bread, you would run out of both at the exact same time. And that would be called a perfectly stoichiometric sandwich making. So in a reaction, if you run out of both reactants perfectly, you have the exact amount that you need, that's called a perfectly stoichiometric reaction. But never really happens, right? So I don't know what that pop-up is. It keeps happening. I gotta look into that. Sorry. So we run out of one before the other because nothing's fair in this world, kid. Okay, so let's do a problem where we would need to consider our limiting reagent. And I'm just gonna go ahead and bring this over to our other slide. Okay, so here's your problem. We have 8.04 grams of iron and 22.3 grams of oxygen react to form iron 3 oxide. How much iron 3 oxide is produced from this reaction? I don't know why I capitalized iron there. That's a little annoying, but that's okay. Okay, so we're going to go through all of the steps of our stoichiometry problems basically twice. But before we can do anything, we have to have a balanced chemical reaction. You can't answer any questions about reactants to products or anything like that unless you have a balanced chemical reaction. So we have iron combining with oxygen. Right? Remember, oxygen is always going to be a diatomic. Why are you forming a triangle now? Okay, hopefully that stopped. Okay, there we go. So iron and oxygen going to iron 2 oxide. So that 2, or iron 3, excuse me, that's what I wanted it to be. So if it's iron 3 oxide, we know that oxygen forms a -2 anion, so we're gonna need 3 oxygens, 2 irons. So now we have to balance our equation. Would be 2 over there. Did I do that right? Yep. So Well, let me just go through that thought process with you. So if it's Fe2O3, this is always going to be an odd number unless it has a 2 coefficient in front of it. So I was going to start with iron, and then I realized that that was going to be my next hiccup. So because these two are iron and oxygen, sorry, you can't see what I'm pointing to, because they are just standalone, I'm just going to do whatever I need to do to my products in order to make it all balance out. That's called familiarity with chemical equations. Hopefully you've built up enough that you're like, oh yeah, that makes sense. I would do that too. So that means that I need 3 of my O2 and I need 4 of my iron. Right, everything checks out. We're looking good, right? I have 4 iron, I have 6 oxygens on both sides. So I'm like, yes, okay, my chemical. So once you're done here, you want to be like, do I have the right formulas? Right equation? Right? Have you written those correctly? That should be like your first check, because if those aren't right, then everything else that you solve is going to be wrong, right? Okay, so I'm given information, I'm given a mass of this reactant and of this reactant, and now I'm asked how much of this is produced. And this is always going to be your situation when you need to consider limiting reagent. So I like to call these red flags. It's like your warning that you're going to have to do more work, right? That's a red flag. Red flag. Is you're given information for 2 reactants and you're asked to solve for product, right? This is always the form that a limiting reagent question is going to take. So anytime you read something like this and then you write the equation, you're like, oh, I have information about this reactant and this reactant asked for this product, you should immediately be like, limiting reagent problem for sure. Okay, so we're just going to solve this the long way around, and then you can find shortcuts by comparing mole ratios, but we're going to do it the long way, because the long way is actually only like 30 seconds longer, and you're always right if you do it the long way. So do it the long way until you're like feeling really good about your mole ratios. Okay, so we have 8.04 grams of iron. And so what I'm doing now is basically like an educated guess and check. So what I'm going to do is I'm going to figure out how much iron oxide is going to be formed from all of the iron that I have. And then I ask the same question, but from all of the oxygen that I have. So first I'm just solving for iron because that's what's written first in my chemical reaction, so why not? So iron, 55.845. Right, and there are 4 moles of iron for every 2 moles and then Fe2O3, 55.845 times 2 plus 16 times 3. I get in 1 mole of Fe2O3, it is 159.69 grams. All right, and I'm going to just go ahead and solve that now. Paying attention to your order of operations, I get 11.58 grams of Fe2O3. Okay, so that is with every single drop of milligram would be more appropriate, of my iron being consumed. So now I'm going to ask the same question, but with oxygen. So I have 22.30 grams of my oxygen. there are 32. What is happening? It's like some shortcut I'm not familiar with, because why would it exist? So you have 32 grams of oxygen are in 1 mole of oxygen. There are 3 moles of oxygen in every 2 moles of Fe2O3. 1 mole of Fe2O3 contains 159.69 grams of Fe2O3. All right, I'm just going to make sure, because that seems like they are very, very different. And that's, for me, I'm like, did I plug something in wrong? Know thyself. No, it's right. Okay, so when you've solved for both of the reactants to figure out how much product you can form, then what you're doing is you're comparing these two answers, right? So on the one hand, if all of your iron is consumed, you have 11.58 grams of your iron oxide. On the other hand, if all of your oxygen is consumed, you get 74.19 grams. But remember, we know from our balanced chemical equation that the only way for us to produce iron oxide is if we have a 4:3 ratio of iron to oxygen. So here, when I look at these two values, I know that the correct answer is going to be the lower number, right? So what I just boxed in here is my answer, because it doesn't matter that I could produce a ton of iron oxide from my oxygen. I ran out of iron before I could ever get there. So when you solve for this, you want to think about that relationship, right? You want to, in the end, if you do it this way, do it the long way. Really, if you look at this, like these two are identical. Everything is kind of the same. Well, everything is identical here and here. So the quick way of solving this is to look at your mole ratios. So I have 4:3 to 2, and from that you can figure out, just by looking at your grams, what species is going to run out first. It's less clear in this example, but let's just not even worry about that. As soon as you have to get to moles no matter what, though, so you can look at your mole ratios, but again, it really doesn't save that much time. So after you've answered this question, bottom line, which one is less, that's your answer. Limiting reagent, whichever one you made less of, that is your answer. So then the question might be, what species was your limiting reagent? It's whichever one you started with that gave you the least amount of product. So iron would be our limiting reagent here. All right, let's do one more for funsies, and then we just have one last little note to finish this chapter on. And then we move into chapter 4. So I said this in the announcement yesterday, but you really want to work towards completing chapter 3 by like Wednesday of next week, so that you have plenty of time with chapter 4, because chapter 4 is pretty involved. Okay, so how many grams of sodium chloride can be obtained from reacting 18 grams of sodium, 23 grams of chlorine? All right, so first thing we have to do, write a balanced chemical reaction. So we have sodium plus chlorine. Remember, chlorine is group 7A. That's a halogen or halide. In this case, it's by itself, so it would just be a halogen. I'm going to make that clearly an L so it doesn't look like Ci. So it is going to form a homonuclear diatomic molecule. So those diatomic molecules are really important to know, because if you just wrote regular chlorine there, your mole ratios are going to be off. All right, so I need 2 and 2 to balance. 2 sodiums, 2 chlorines, feeling groovy. All right, so notice I have the same situation as I had last time, given information about 2 reactants, asked for information about a product, red flag, limiting reagent, right? You can like hear a ref blowing a whistle, maybe. That's the only sports analogy I've ever successfully made in my life, so feeling pretty good about that. Okay, so we have 18 grams of sodium. Right, so we have, what is it, 22.99 grams of sodium are in 1 mole of sodium. There are 2 moles of sodium for every 2 moles of sodium chloride. Sodium chloride, 22.99 plus 35.453. It's 58.44. Oops. See, this is where checking your work makes a lot of sense. My moles are not going to cancel out with my grams. I just got excited for finding molar mass. So this is where the picket fence is really great, right? It's always 1 mole for molar mass, 58.443 grams. It's such a simple mistake to make. It's so easy, and that's where this picket fence, I think, is just really great. It's the way Mrs. Burr-Michael taught me. Okay, so that's what I get if every single milligram of my sodium was used up. Now let's solve the same problem with my chlorine, 23 grams. All right, 35.453 times 2, 70-something, 70.906. Second one's always faster to solve because you already have the molar mass found. Okay, so now we have that same consideration, and ultimately, just in a nutshell, whatever reactant produced the least amount of product is your answer for the amount made. So for this question, the only thing we're looking at is the grams of sodium chloride that can be obtained. So your answer is 37.91, right? 45.76 is incorrect. Why? Because we ran out of chlorine before we could get there. So just really quickly to kind of show you how you would think about the shortcut version of this, which is just kind of a fun thought experiment. So for sodium, you need to get to moles no matter what. So you convert your grams to moles. So we know that we have, definitely don't want to be in a highlighter anymore. Okay, so we know that we have 0.78 moles of sodium. And then we have 23 grams of chlorine. Divide that by its molar mass. Okay, so this is the number of moles we have, right? And we needed to get to moles. We cannot just look at grams to figure out what's going to run out first. It doesn't matter that I had 18 grams of sodium. I have fewer grams than chlorine. That's irrelevant, right? Because grams is not comparable between species. Moles is. So I have 0.78 moles of sodium. I have 0.32 moles of chlorine. I have a mole ratio of 2 to 1. So I ask myself, do I have more then 2 times as much sodium than chlorine. So 0.32 times 2 is 64, 0.64. I have more than 0.64 moles of sodium, which means that I have more than 2 times as many sodium molecules as chlorine molecules. So just by looking at that, I could say, okay, chlorine is my limiting reagent, and all I would have to do is solve this problem. Is it any faster? No. Is it more fun? Yes. Would I recommend doing it this way? Yes, for a while. But this is more fun. Right, because then you're looking at relationships. We like that. Okay, so we have 37.91 grams of Cl2. I'm going to write that down so I don't forget. 37.91. I would remember that, but just in case. Okay, that's about our grams of sodium chloride that we produce. The reason why I want to write that down is it's going to become relevant in our next slide. So there's one last thing that we want to consider, and that is that stoichiometry is not reality. So in all of the calculations that we've done in this lecture, the assumption is that 100%, like in the last example, 100% of that chlorine was used up in producing sodium chloride. But really, no reaction is 100% efficient. Why? Because it's one of the laws of thermodynamics that there's no such thing as 100% efficiency of any system ever, right? Fundamental law of our universe. Things get lost in the move, right? We all know this. It happens. So it's also true for molecules. It's going to get lost to the environment, or if it's energy, you're going to lose some heat. So no system is 100% efficient. And so we have this concept of percent yield. So we've already worked with percents in this class in our first lab, that density lab. So remember, a percent is always a part over the whole times 100 equals your percent yield. Or it just equals your percent, right? If I didn't have yield there, it could be any percent equation ever made in the history of our planet. So what we're doing here is we're looking at, okay, what does stoichiometry say that we'd make, and what is reality? Right? So from that last problem, we said that every single microgram, every single atom of chlorine was used up in that reaction, and we got 37.91 grams. This is our answer from stoichiometry. And this is also called our theoretical yield. Right? This guy. So, in order to figure out what our percent yield is, we'd have to be told what the actual yield is. Or we'd have to be told the efficiency of the system, right? So you have to be given one of those two pieces of information, otherwise you would have a multivariable problem. So let's say in our problem we say that after the reaction runs its course, we get 30.7 grams of NaCl is actually produced. Right, so this would be our actual yield. So to figure out what our percent yield is, it was 30.7 was our actual over our 37.91, right? So from stoichiometry, stoich, and this is what we were told, times 100. We get an 80.98% yield. Now, is that good? I mean, for sodium chloride, sure, right? Because that's, I mean, 80% yield is pretty good for pretty much anything. But those aren't expensive reagents, so 80% yield, I'd be happy with that. But for some processes, that percent yield is like unimaginable. So the combustion engines, even the most efficient ones today, I think, are less than 30% in their efficiency. So 70% of gasoline is just getting burned up and just slowly killing our planet without any work being generated from it. Sit with that for a minute, huh? Okay, so this is one way that you could solve percent yield. Another way would be like, okay, so we had that 37.91 grams from the last problem of sodium chloride were produced. So you could be told that the system of production is 60% efficient, right? So then the question is, how much was produced? So here we would have our percent yield and we would have our theoretical yield, but we don't have our actual yield. So we just want to rework that problem, right? So it would be our percent yield, 60%, times our theoretical yield, that's at 37.91 grams, divided by 100 would give us our actual. So 60 which is 22.75 grams. All right, and that's it for chapter 3. Every single thing from this chapter is going to be applicable to chapter 4. So make sure you spend some time on it. My advice for you is this next quiz is going to be, this material is more challenging, so the quiz will be more challenging. So before you take the chapter 3 quiz, I would make a consolidated sheet, like a cheat sheet, if you will, of your notes, so that when you're taking the quiz, everything is right there for you. So when I teach this class in person, every quiz, students get 1 page of notes front and back, and every exam they do as well. So I would really recommend for chapter 3 that you prepare that sheet. It's a good way to study. And it's also just a good practice, right? So if you're taking this online or if you're taking it in person, it's just good practice. Okay, that's all I got for you. Chapter 4 is next.